Let us discuss a problem on the Rayleigh's approach. A statement is like this: a steel rod of 10 millimeter diameter and 200 millimeter length is subjected to two equal forces of magnitude 10 kilonewton at the midpoint and at the end. The modulus of elasticity for the steel is 205 gigapascal. Use the Rayleigh's method to determine the approximate function for the displacement, the approximate function for the strain, and the approximate function for the stress. So look at this geometry. So it is a rod of length L, midway between along the length it is carrying a load F. XY coordinate frame is shown. So for general deformation, strain energy in the rod per unit volume is, we know, as area under stress strain curve, 1 half sigma into epsilon. U equals to 1 half sigma into epsilon. So total strain energy is the integral of this strain energy per unit volume U into dV over volume V. So it gives an integral from 0 to L 1 half sigma into epsilon dV. So again, after simplification of this integral, sigma is E into epsilon and dV is A dx. So it will take a form integral from 0 to L AE by 2 dy by dx square into dx. Take e by 2 outside integral, so u is e by 2 integral 0 to L du by dx square of bracket dx. So work potential due to applied load is given like this. So F is load, right? So work potential V equals to minus F u L by 2. So at L by 2 work potential is minus Fu, and at the end it is minus FUL. So total potential energy is pi, that is equals to U plus V, U being the total strain energy and V is the total work potential. Now looking at the boundary conditions at x equals to 0, u equals to 0. So step 1 in this method is you need to assume a displacement function to be linear, quadratic or cubic. For this problem we have assumed this displacement field to be quadratic function. Ux is equals to c0 plus c1x plus c2x square. Boundary condition 1 is like this. Use boundary condition 1 now. So ux is 0, that is equals to c0. c1x is 0, c2x square term is 0, therefore c0 is 0 in this case. Now substitute that value in the equation for ux is equals to c1x plus c2x square. Now du by dx, differentiate this equation once with respect to x as equals to c1 plus 2c2x. Now use boundary condition. Ux at x is equals to L by 2 is, substitute value of L by 2 in this now as c1 L by 2 plus c2 L square by 4, and at ux is equals to at ux at x is equals to L, so it is equals to c1 L plus c2 L square. So as step 2, total potential is equals to pi, that is equals to a by 2 integral 0 to L c1 plus c2 c2 x square of the bracket dx. That is term that we got, right? C1 plus 2 c2 x square du by dx term square of the bracket dx minus f c1 L by 2 plus c2 L square by 4 minus f c1 L plus c2 L square. So simplify again the bracketed terms and get a final form of this in terms of c1 c2. So total potential terms are now like this: pi p equals to e by 2 c1 square L plus 2 c1 c2 L square plus 4 by 3 c2 square L square minus f 3 by 2 c1 L plus 5 by 4 c2 L square. Now step number 3 is set up and solve system of equations, as you have to differentiate now total potential energy with respect to c1 first of all and equate it to 0. Now differentiating the above equation with respect to C1, it gives A by 2 2C1L plus 2C2L square minus F 3 by 2L, that is equals to 0. So you can see how we have arrived at the derivative of potential energy with respect to C1. Simplify this equation to get a simplified form as C1 plus C2L equals to 3F by 2AE as equation A. Again differentiate this the same equation with respect to C2 now and get the second form as C1 plus 4 by 3 C2L equals to 5F by 4AE as equation B. Now from equation 1 above, so you have to substitute these values in that equation and get a coefficient term C2 minus 3F by 4AEL. Use this in one of the equations, either A or B. Simplify that equation and get another coefficient C1 as 9F by 4AE. Now approximate displacement function, it is like this. You have to substitute value of C1 and C2 in the equation for Ux as evaluated above. So this Ux is now the approximate equation for the displacement in terms of load F, area of cross section of rod, E value, and the X value. X is the variable along the length. Now you have to find strain function. As differentiating above the equation with respect to X, you will see to get a strain equation, and stress function is you have to multiply it by E value, Young's modulus, so you will get a stress equation. Now the approximate displacements based on these equations you have to evaluate by making use of load F, A value and E value. So Ux is like this in millimeter, approximate strain is like this, and approximate stress is 95.325 into bracket 3 minus x by 100.